Number 9, it says one way to define the number e is in terms of a limit. All right, so this rather important number e is the base of the natural logarithm, right? It can be defined in a number of different ways. Here we're defining it as the limit as n approaches infinity of the quantity 1 plus 1 over n all raised to the nth power. Okay, so note here that for large n, this expression 1 plus 1 over n is going to be a number just a little bit over 1. And then we're raising it to a really large power. And so what's that going to give us? Well, 1 raised to any power is 1. So something just over 1 raised to a really large power will be something, well, more than 1. And there's a certain balance that happens here, right? The base is approaching 1, but the exponent's approaching infinity. And in that balance, this quantity converges to this number we define to be e. And it's approximately equal to 2.71828182846. All right, so quick visual here. You see the function f of x, which is 1 plus 1 over x all raised to the x power. Corresponding sequence in blue here. Okay, now it's a monotonically increasing sequence, and it's bounded above here in green, and this bound here in green, that's just the number e. And notice here, as I let n increase with the slider, this quantity is approaching this number e. Alright, so nice visual there. So now, with part A, it says, use this limit to show that for a greater than 0, the limit as n approaches infinity of the quantity 1 plus a over n, all raised to the n, is equal to e to the a. Okay, so in other words, if I replace this 1 that I see in the original expression with an a, okay, then this corresponding quantity will converge to e raised to the a power. All right, so now to do this, it's going to be a little bit tricky. I'm going to rewrite this expression as follows. Okay, so first, this a I see in the expression inside parentheses. I'm going to put it downstairs here, so it'll become 1 plus 1 over n over a. And then the n up here in the exponent position, I'm going to break that apart as n over a times a, right? These exponents are multiplying each other by the properties of exponents. And so this all simplifies just back to n. All right, so why am I doing this? Well, the key here is that since a is a positive number, this quantity n over a will approach infinity as we let n approach infinity. So I have 1 plus 1 over something blowing up, all raised to, well, this thing, which is also blowing up. So that's essentially this limit that I see above. Now, to make that a little clearer, let's make a substitution. I'm going to let this quantity n over a equal m. Okay, and as I noted before, since a is a positive number, then m, which is n over a, that'll approach infinity as we let n approach infinity. Okay, so I'm going to replace the limit as n approaches infinity with the limit as m approaches infinity, which is justified by this statement here. And then n over a shows up there and there, so I'm just going to replace those with m's. And see, now this quantity inside will approach, well, just e from this given limit. And so, putting it all together, this thing inside is approaching e, and it's going to be raised to the a power. Okay, so the limit of that expression is, in fact, e to the a. Okay, quick verification of that. Let's say I replace this 1 with a 7. And then I compare that to e to the 7th. Yeah, right? So as I let n increase, yes, it appears that this quantity is converging to e to the 7th. All right, and we've proven that right here. Great. Now for part B, it says, use the result to part A to compute the limit as we let n approach infinity of the quantity 1 plus 7 over n, all raised to the nth power. Well, here, nothing to it. We're just setting a, this number from part A, equal to 7, so the limit there would just be e to the 7th. All right, well, that's going to do it for this problem. Thanks so much.